Thank you for the introduction and thank you for giving me the opportunity to talk here. I'm going to talk about the numerical integration, which also Johan alluded to in his talk. And let me start with the setting. So I'm considering a Riemannian manifold, a connected compact Riemannian manifold, which is assumed to be equipped with a smooth metric tensor G, Riemannian metric, and it is also without boundary. And we consider a function space F, which is equipped with some norm. And the general problem we will consider is how can we find points on this manifold and weights, corresponding weights, such that this cubature rule, which I have here, evaluating the points, the function at the points and combining them to some average, whether this approximates this integral, where this is the measure with respect the Riemannian volume. So this is the Riemannian volume induced by this metric. And we want to find points such that this approximation is good, and by increasing n, it should approximate the integral for every function uniformly. And to make this a bit more precise, I restated here in some different forms. So we want to find points and weights such that this worst case error, where the worst case error is formed over the unit ball of this function space, is small. And how small can it be? So as a measure of comparison, we use this minimal error. So we minimize here over all point sets on this manifold, which have n points, and minimize over all real weights. And we consider this minimal error, and we want to find points and weights such that we come close to this error. So let me briefly give some example, maybe, because before we often have seen equal weight integration rules, so the weights are all equal to 1 over n. And spherical designs are a prominent example of such rules. For this example, we use the sphere as D and equip it with its usual metric, so that we have the geodesic distance and the uniform measure sigma. And we consider the space of polynomials on the sphere of degree at most t. And then a T design is a point set on the sphere which integrates the polynomials of degree up to t exactly. So we do not make an error on this function space. And now the question is, so this is some strict requirement, and when can we find point sets like this? So the number of points must be at least t to the d. This is due to a lower bound, which was already mentioned in previous talks by the Oates and Seidel. And also there's a corresponding upper bound by Bondarenko, Varchenko, and Wiercowska. And this shows that we can expect such designs for number of points strength to the d. So here I mean with this equivalence that we find constants, small c and large c, such that we can bound these sequences. And I'm always going to be talking about this asymptotic kind of equivalences. So I will not be interested in exact constants, but rather in rates of decay and asymptotic equivalence. And these spherical designs are very useful for integration in other function spaces, which are defined via spherical harmonics. And here I give the definition of a Sobolev space of integrability P between 1 and infinity and smoothness S greater than D over P. And this definition looks rather abstract, I admit. So let me explain a bit. We consider functions which are P integrable on this manifold, and then this operator applied to the function F should be still in LP. And here this delta is the Laplace-Beltrami operator, which many of you already know. And this Sobolev space is basically just the space of functions such that the S derivative is P integrable, So this functional calculus just says you something like that. And this smoothness condition S greater than D over P just ensures the continuity of these functions such that we can evaluate them and consider these cubature rules. And now there's a result that these spherical designs I mentioned earlier with this optimal number of points, order optimal number, that these equal weight cubature rules attain the optimal behavior. So the error is asymptotically optimal in the sense that it is asymptotically equivalent to the minimum over all point sets and arbitrary weights. And this weight is n to the s minus n to the minus s over d. We will encounter it later. Okay, and now we have found some optimal designs in this case. So the question seems to be solved then, because we already have found these optimal points. Why look further? Yeah, so maybe the case can, we consider here the case that the data cannot be chosen by ourselves. So one reason for this is that these designs are difficult to find and compute for larger and larger n. And maybe the data is given by measurements from outside. So we just have the data and have to approximate the integral from this. And these points which we get may be random samples. So this is a common assumption in machine learning, for example. And then we want to know the following. So we have some point set given on this manifold. And we ask ourselves, so what are good weights? How should we choose the weights to integrate functions in Sobolev spaces? And meaning we want to minimize this worst case error over all cubature rules which use this point set and some weights. And we want to ideally find weights minimizing this expression, or at least up to a constant. And we also ask the question, how good is Pn, this given point set, compared to the optimal n point sets, like spherical designs on the sphere? And we want to measure the quality of such point sets by this minimal worst case error. And how could we do that? So a common approach is to use the following. Namely, we consider the geodesic distance on this manifold and then define the distance of a point x on the manifold to the point set Pn by taking the minimal distance to all points of Pn. So we take the closest point and measure the distance. And this is the distance function. And now we can define the covering radius, which was already present in several earlier talks, which is just the supremum of this distance function. So it's the radius of the largest hole in this point set. And with this geometric notion, one can bound this quality of the point set with respect to numerical integration like follows. So there's a result by Ehler, Gräf and Oates, that there exists a constant such that for any point set Pn, we can bound it by this constant times the covering radius to the power of s. And you maybe already know that this covering radius is in the optimal case of order n to the minus 1 over d, and to the s means just n to the minus s over d is this upper bound. This is for optimal points, but in general, we have only the following characterization. So there's a complementing result also with Krieg, and then we can get the lower bound, which extends previous results from the sphere, where we have an order in the covering radius of s plus d and some additional factor depending on p. And if we consider a covering radius which gets very small, we lose here something. And this is already also sharp. So in general, this cannot be improved. And it seems that the covering radius is not the right quantity to measure the quality of point sets for numerical integration. So what kind of geometric notions could we use else? Yeah, and in our result, we looked at the average distance instead of the maximal distance, so to speak, where we look at the distance function and take an L gamma norm of this. So it's an average with respect to the volume measure on the manifold. And using this quantity, we could show that for any P, points at P, we have this asymptotic equivalence, namely that the minimum over all weights of this worst case error, so the quality of this point set for numerical integration, is asymptotically equivalent to the L gamma norm of the distance function to the power of S. And this is from above and below. And this asymptotic notation means here, it's written down here, that we have constants such that we can bound the left-hand side by the right-hand side from above and below for any point sets. These constants may depend on S, E, P and the manifold, but not on the point set. And here this gamma depends on S and P in this way, so P star is the Höller conjugate of this parameter P. And I just want to give some brief details on the proof. Namely, for the upper bound, we have to exhibit these optimal weights such that we can achieve such an error. And we used a smooth partition of unity to localize our functions and use an,
Yeah, sorry, a quick question. The previous result, was that on any domain or is it just on the sphere? Sorry, I forgot by now. What's the domain? It's any metric,
yeah,
any metric, compact metric space.
It's a manifold, compact manifold.
Yeah. Okay. Yeah. Thank you. Sorry.
Yeah. Right. And in the proof, we also used this Riemannian structure that it's locally like Euclidean space. Namely, in the second step, we used the exponential map to transfer this distance to the Euclidean distance, and yeah, the Riemannian metric enables to compare this. And then we use an efficient covering by suitable cubes. So the details are in a precursor paper by us. And it's a technique which I won't describe in detail here, but let me say just that it uses local approximation by polynomials on these cubes, which are in the covering. And then we can reconstruct these polynomials on these small cubes via least squares algorithm. This gives us the upper bound. And for the lower bound, we use a common approach via fooling functions. So we use a function which vanishes on the point set and has small norm and large integral. For the construction of such a function, we again use the Riemannian structure and map from the Euclidean space to this manifold. Now let me say something about this central quantity which we use to characterize the quality of our point sets, namely this average to the gamma, so this integral, is also known as the distortion of this point set Pn, and it is also studied in quantization theory and also in optimal transportation, and it was already mentioned, I think, by Alex Vlasiuk, that how this arises as an error of an of quantizers in general. And one can show using this theory that the optimal points, or maybe using this theory, one can obtain precise asymptotics here, but we are interested only in asymptotic equivalence and see that the optimal rate is again n to the minus 1 over d. And so we obtain the following characterization for optimality, namely that the sequence of point sets is asymptotically optimal for numerical integration in the Sobolev spaces if and only if for this special parameter gamma, we have that this distance function, average distance, behaves like n to the minus 1 over d. And this is in fact an improvement over previous results as we saw. So let me briefly discuss the result. Namely, we call it here, we have the characterization here. And originally in this precursor paper, we derived it for convex sets in RD as our domains instead of manifolds. And let me say that we also obtained a more general result for LQ approximation instead of integration, but I wanted to focus on integration for the sake of simplicity here. And basically it says that for Q smaller than P, there's an average distance occurring. So average distance for where the gamma depends then on Q. And for Q larger than B, there's the covering radius. So there we really have to use this covering radius. But for integration, this case does not appear here because we only look at P larger than 1. And yeah, what about these boundary cases? So we considered only P between 1 and infinity because yeah, we used an equivalent characterization via partitions of unity. And there it is, I think, not known or not true that this also holds in these boundary cases. So one would need maybe a different method to prove it. But intuitively, what do we see? If P tends to 1, then gamma tends to infinity, and we approach the covering radius to the power of S. And for P tending to infinity, we approach just the S, yeah, LS norm to the S. And let me give you an example. In this case, so I'll be considering Lipschitz functions here. And technically, these are not Sobolev spaces, but they behave in some sense very similar. Namely, we define a semi-norm of functions like this. So just take the difference between function values and divide by the geodesic distance. And then this function space corresponds to the Sobolev space of smoothness 1. So we take first order differences and take the supremum norm. So it's corresponding to H1 infinity. And here we can obtain something even stronger if we to only consider the semi-norm. So this is a well-known result. One can derive it using different techniques, but it can be computed relatively easily. So if we take here a point set and consider Lipschitz functions, then the quality of this point set for numerical integration is exactly equal to this distance function in average. So here is a 1, and this 1 corresponds just to the S equals 1 and P equals infinity. And the lower bound is quite easy to see. So we insert this function, this distance function, and then the first term is 0 because the distance function is 0 on the point set. And the second term is just the integral. And this gives the lower bound, for example. For the upper bound, one has to maybe think a little bit to arrive at the following optimal cubature rule. Namely, one can take as weights the volumes of the Voronoi cells of this point set. And this is because the Lipschitz functions cannot grow faster than the distance away from the point set. And it makes sense to split up the domain, so the manifold in this case, into these Voronoi cells defined here. So for each, we take for each point in the point sets the collection of points on the manifold which are closer to this point than to any other point of Pn. And if we take then the volume measure of these Voronoi cells, this gives the optimal weight. So if many points are close together, the Voronoi cells will become very small. So the weights are rather small. The point's not so important, but one point far away from the others has a large weight, which kind of is intuitive. Now a question is are these weights also optimal for Sobolev spaces? I mean, we have computed some weights, but they are not very intuitive and we have not an explicit expression for them. And now the question is, can they be expressed in such a nice way? So yeah, would be interesting to know. And now I come to some other topic related, namely, we can look at random points now. And random points also were mentioned in Mario's talk, where they gave optimal order, near optimal order, but yeah, the best results known. And here we can also consider random points, which are independently and uniformly distributed with respect to this Riemannian volume measure. And it's well known that the Monte Carlo rule, so if we take equal weights, the average error will be n to the -1/2 asymptotically. And now the question is if we optimize over the weights. So if we look at the quality of this point set, of this random point sets, then on average, one can show that this is bounded by n to the -s/d times this logarithmic term using the result by Ehler, Gräf and Oates I showed you before, and that the covering radius is of size n to the -1/d times this logarithm to the 1/d. So here we have a suboptimal bound, and it would be interesting to know if random points attain, in fact, the optimal weight n to the -s/d. And Ehler, Gräf and Oates also stated such a question. And now using the characterization I showed you before, and the following fact, namely we have to compute the distortion of these random points. This has been done for Euclidean spaces already, for example, by Cohor. And we imitated the proof to get the following result, namely that the random points satisfy that multiplied by the weight one would expect, so n to the gamma/d, then this converges to a constant in LP sense for p between 0 and infinity. So this quantity to the gamma, this is the average distance to the gamma, is n to the -gamma/d. So the optimal rate on average. And using now our characterization, we get that on average, we have here the optimal rate of n to the -s/d. And to summarize, for these random points, we see that they are asymptotically optimal for numerical integration in Sobolev spaces for these parameters, which is kind of interesting to know that one does not have to look for the specialized point sets if one is willing to compute the weights, which may be a difficulty in itself, but I do not discuss this. Now, I want to talk about the second application, namely on the spherical discrepancy. And let me introduce some related notions. So now we consider the Euclidean distance on the sphere, and again, the rotation invariant measure sigma. And on the sphere, one uses commonly the system of spherical caps defined here. So these are intersections of the sphere with half spaces. And one can look at the spherical cap discrepancy, which is as follows. So one looks for each cap at the proportion of points inside and the difference to the actual measure of this cap. And one takes the supremum over all caps. And now for the L2 discrepancy, one does not take the supremum, but in fact the L2 norm over this parameter space. So for the L2 discrepancy, we have the following expression. It's written down here, so as before, but instead of the supremum, an L2 norm. And then I want to mention Stolarsky's invariance principle, which was already mentioned by Johann Brauchert in the previous talk, and I think also before, last week, for example. And it states that this discrepancy squared is an energy difference, where we have this energy kernel with the Euclidean distance. And now I'm interested in a weighted analog because there's a result by Brauchert and Dick. So one can use the expression for the reproducing kernel of a special Sobolev space, namely space of smoothness d plus 1/2 on the sphere. And then one can show that the worst case error of any cubature rule is equivalent to the L2 discrepancy, to the weighted L2 discrepancy, which I define like this. So instead of taking equal weights as before, we take here the weights. And basically this means this is the integration error on a single cap inside, and we average this over all caps. And yeah, this is then equivalent to the worst case error. Yeah.
How do you choose the weights here?
Here, this is general. For general real weights.
So you're saying
sum up to 1, or?
They don't have to sum up to 1, I think.
okay, if they don't sum up to 1, then probably the error on the left-hand side is bad, and the right-hand side is
Yeah.
okay.
I
So,
think,
so it's just the same weights in the discrepancy and in the integration, right?
yeah.
Okay,
Yeah.
okay, makes sense.
Yeah. Right. Okay. Yeah, but for the following, I want them to sum up to 1, namely if one wants an analog of Stolarsky's invariance principle, one assumes that the weights sum to 1, then one can compute that this weighted discrepancy squared is in fact this energy difference, where we take not the measure putting equal measure on the points, but weights. And then our characterization from before implies, so this weighted L2 discrepancy is a worst case error in a Sobolev space, and we have, if we minimize over the weights, we have an expression. Namely, we have this average over the distance function, where we have now the Euclidean distance function with this power e plus 1. And in fact, we can restrict the infimum to here in this expression to only weights summing to 1. So yeah, one may lose a constant by this, but we are not interested in constants. And then one can insert this energy difference here, and one sees that the minimal energy difference, if one minimizes over all weights summing to 1, is in fact asymptotically equivalent to this average distance to the power d plus 1. And with this result, I want to end my talk.